All right, so section 6.3. Sampling distributions and estimators. So we now consider in this section the concept of sampling distribution of a statistic. So far, guys, throughout the course, we talked about three sample statistics. When we collect sample data, we use the sample data to get three numbers. We get three sample statistics. And these sample statistics, the first one, obviously the most important one, is the sample mean. Number two, the sample variance. And number three, the sample standard deviation. S. Right? So each and every sample we take from the population is going to give us these three statistics, which are very important in the analysis of our data. We use these numbers here in a lot of statistical methods in order to, come up with a conclusion or some statistically significant results about population that we got the sample from. So these sample statistics are very important, and today we're going to discuss the distributions of these samples, distribution of sample. Okay, explain first objective. Distribution of sample means. So let me just visually talk about this, and then I will give you the technical or the statistical definition of this distribution. So suppose I have this set here, population set. Population, and let's assume that we gonna select all the possible samples of the same size. We select all the possible samples of the same size. So let's say our sample size is n, and we're going to select all of the samples of size n. Sample 1, sample 2, sample 3, and so on. So each one of these samples will give us a sample mean. So the first sample will give us x1 bar. Second sample, x2 bar. Next one, x3 bar. x4 bar. x5 bar, and so on. So now these sample means become our data. We have a set of sample means. Right? We take every and each sample, all of them of the same size, sample size, same number of values. We calculate the sample means. Now we have a set of sample means, x1 bar, x2 bar, x3 bar, and so on. Right? Sometimes the set might have like, 100, 200 samples. So a large set of sample means. We have a bunch of sample means, and our interest and we're going to be concerned with how do these sample means, if I graph them or if I do a distribution for those sample means, how the sampling distribution will look like. We want to talk about the shape of the distribution of sample means. Right? So we selected all the possible samples from the population. All of them have the same size. Each one gave us a sample mean. Now we're going to look at the spread or the distribution of these sample means. Okay. So now here's the technical definition. Let me just quickly take a picture of the definition so we don't have to spend a lot of time writing it. So again, we're talking about the sample means, and the technical definition says the sampling distribution of the sample mean is the distribution of all possible sample means You can also say the distribution of the variable X bar with all samples having the same sample size taken from the same population. We take all the possible samples of the same size from the same population, and when we collect these sample means, and then we look at the distribution, the spread, how are they clustered together? Are they spread out? Are they, we want to discuss the behavior of this statistic. This variable, the sample mean, is very important. We want to learn more about how these sample means how we can describe them. We try to get more information and insight on this statistic. Okay. So we notice the following: the behavior of sample means can be summarized in 2 points. The first observation that we have is that the distribution of the sample means tends to be a normal distribution. That's a very important result. Okay. So the distribution of the sample means is most likely is going to be a normal distribution. It has a bell curve, but we're going to talk about this a little bit more later. Okay. This distribution tends to become closer to a normal distribution as the sample size increases. So again, going back to this illustration here, we have a set of sample means. We notice that if we look at the dot plot of this set, we notice that these sample means, if you represent them by a dot plot, you will notice that these sample means is going to give us a normal distribution like this. Each dot here is a sample mean. And we notice that the distribution of these sample means is going to be a normal distribution. Maybe for small samples, it's not going to be perfectly normal, but as the sample size gets bigger and bigger, and we collect these sample means, we look at their distribution, we notice that the distribution becomes more and more normal distribution, or more, it goes towards a normal distribution. So that's one observation. Also, we notice the following, that the sample means target the value of the population mean. This is also a very, very important result. It talks about the center of this normal distribution. The mean of the sample means is the population mean. So if I look at the center of this distribution of the sample means, the center, which is the mean of all sample means, is the population mean. Remember, we use mu for population mean. That's a very, very important result. the sample means target the value of the population mean. So that tells me that the all of these sample means are clustered around the center here, and that center is actually the population mean. See how close they are to the they are very concentrated about the center here, and the center is the population mean, right? These samples came from a population, and those sample means are clustered or about around the population mean. So I think of, you know, the population as the mother and the samples are the children, and the children are around the mother. They have similar characteristics or similar values to the sample means have values very close to the population mean. And it makes sense, you know, because all these samples came from the same population. All right. So two things, two observations. The first one is the distribution of the sample means. Most likely is going to be a normal distribution. And the second one is the center of that distribution is the population mean. Okay. I'll give you an example just to emphasize the concept. Example. Suppose I give you, or I suppose I have population set only 3 numbers. Let's say the population is only 3 numbers, 3, 5, 9. This is the whole, this is the complete set, population set. Now, what if I select all possible samples of size 2? Right? Let's consider all of these samples. All the possible samples taken from this population. Okay, so I'm going to make a column here, sample and sample mean. We're going to talk about all possible samples taken from this population. We're going to consider that these are samples taken with replacement. So repetition is allowed in the samples. So for example, 4, 4, 4, 5, 4, 9, 5, 4, 5, 5, 5, 9, 9, 4, 9, 5, and 9, 9. Right? I can't think of any other possibility, guys. These are all the combinations, or these are the possible subsets of 2 elements taken from the population, right? You can't think of anything else. Now, let's go ahead and find the sample means for each sample. 4 and 4, 4 plus 4 divided by 2 will give us 4. This first sample mean is 4. Second one is 4.5. 4 plus 9, 13, divided by 2, 6.5. 4.5, 5. Continue. Uh, 14 is give you 7. And then 13, 6.5. And then 14, another 7. And then 9. Right? So I'm going to now make a list of all of these sample means. 4, 4.5, 6.5, 4.5, 5, 7, 6.5, 7, 9. Okay. This is all the sample means, right? All of them. Now, what if I find the mean of these sample means? What if I add them, all of them, add and divide? See here, notice I'm adding all the sample means and then divide by the number of samples, by their numbers. How many sample means do I have? 3, 6, 9. I take this average of the sample means. So let's see what it is. Let's add these values. 4 plus 4.5, 6.5, 4.5, 5, and then 7, 6.5, and 16, 54. And then I divide by 9. That will give me 6. So that's the mean of the sample means, of all the sample means. Now, let's go to the population and find the population mean. My population is 4, 5, 9. So I take those numbers, 4 plus 5 plus 9. And then I divide by 3, 18 over 3, 6. Same. So the average or the mean of the sample means is equal to the population mean. That's why I'm saying that the sample means target the value of the population mean. The sample means target the value of the population mean. Okay. Any questions, guys, on this concept?
Another question.
Yes, go ahead, please.
For the mu, where did you get the 4, 5, and 9 from?
Hold on one second. Let me raise the sound a little bit. Go ahead again, please.
For the mu, how did you get the 4, 5, and 9 divided by 3?
Oh, yeah. This
Yes.
here, this is the population mean. And the population is here, the original set. You see those samples that I found? These samples came from this set. So I wanted to find the mean or the population mean, the average of the original set, the population. So 4 plus 5 plus 9, the sum divided by 3, because I have 3 numbers.
All right, thanks.
You see it?
Yes, that's perfect.
Okay.
Professor, for your X bar values, how did you get those?
The X bar values, you're talking about those values?
Yes.
Yes, those are the sample means. And let me show you how I got the first one. See, this is my sample right here. I add the values, divide by 2.
Okay.
4 plus 4, 8, divided by 2, 4. 4 plus 5, 9, divided by 2, gives us 4.5. Just the average of, or the sample mean.
Okay. Thank you.
Mm-hmm. So this is just an example that shows or illustrates that the sample means are clustered around or concentrated about or around the population mean. Now, this observation that we see in the sample mean also appears in the sample variances. The sample variances behave the same way. Okay. So I want to talk about this next distribution, which is the sampling distribution of the sample variance. All right, let me explain, guys, or let me again give you the definition. So now we're going to consider the sampling distribution of the sample variances. The sampling distribution of the sample variance is the distribution of sample variances, the distribution of S squared, with all samples having the same size taken from the same population. Okay. And again, we notice that the distribution of the sample variances will also be, will look like a normal distribution, a bell curve. All right, let me show you again another picture to clarify the concept. Again, this one here is a good one. So here we have an experiment, which basically rolling a die 5 times and find the variance of each sample. So we roll the 5, we get 5 numbers, and then we find the variance of these numbers. So notice here, this is sample 1, and then this is this sample variance. Sample 2, sample variance. For each sample, we calculate the sample variance. And then we notice that the sample variance tends to have a kind of normal, but actually with more values, it looks like, I'm sorry, it's skewed distribution. Skewed distribution. Now, the population variance is 2.9. And if we take the mean of the sample variances, right, the mean of S squared, if we collect all of these sample variances and find their average, the mean, we notice that the mean of these variances is the population variance. So in other words, again, the sample variances target the population variance. The mean of all sample variances is equal to population variance. So again, the sample variances are concentrated around the population variance, so they target the population variance. Let me show you guys an example here. I'm going to take this table. I'm gonna erase these numbers. I'm gonna replace this with S squared. And remember, S squared is the sum of all the squares, the difference of the squares of the differences, x minus x bar squared over n minus 1. Now in this case, n is 2, so therefore n minus 1 is 1, so the denominator becomes 1. So this becomes, in this case, just the sum of the squares of the differences, x minus x bar squared. Okay, so let's say if I want to calculate the variance of the first sample, first value is 4, subtract the mean, which is also 4, second value is 4 minus 4, square the differences, I get 0. If I do the second value, second variance, what is the average here? 4.5. So 4 minus 4.5 squared plus 4 plus 5 minus 4.5 squared. So that's 0.5 squared plus 0.5 squared, and I believe this is also 0.5. You see what I'm doing here? So I found so far two variances. The first one is 0. The second one is 0.5. Let's continue. So we found this variance here. Second one is here. Now the next one, the mean in this case is what? 6.5, right? 13 divided by 2, 6.5. So 4 minus 6.5 squared, and 9 minus 6.5 squared. That will give me times 2, 12.5. The next one, 5 and 4, the same as 4 and 5. This one I don't need to do anything, just use the same number I got before, 0.5. 5 and 5 is 0, the same as 4 and 4. Uh, 5 and 9, what is x bar? 7. Right? So 5 minus 7 squared, 9 minus 7 squared, and that is what? 4 plus 4, 8. So that's my next variance. So far I have 6. And then the next 3. The next 3, 9 and 4, same as 4 and 9, 12.5. 9 and 5, same as 5 and 9, this is 8. And then 99 is 0. Right? So I got all my sample variances. I have 9 of them. All the samples. sample variance. What did we get, guys? 0, 0.5, 12.5, 0.5, 0, 8, 12.5, 8, 0, 3, 6, 9. Right? These are my sample variances. Now, what if I take the average, the mean of these variances? I'm going to add them. 0 plus 0.5 plus 12.5. And then divide by 9. Let's see here, 12.5 plus 12.5 plus 1 plus 1642 over 9, 4.666, so I would say 4.7. This is the average of all sample variances. Okay. Now, what is the population variance? Our population set is what? The three original numbers where we have 4, 5, and 9. What is the population mean? Population mean is, we said, 6. So what is the population variance? Remember, the population variance is the sum of x minus the mean squared over this population size. Population size is 3. Not the square, guys, just the sum. Correction, because the square will give us the standard deviation, just that. So the population variance is the sum of the differences squared. So 4 minus 3 squared, 5 minus 3 squared, and 9 minus 3 squared over 3. So that gives me 1 plus 4 plus, this is 636 over 3.
Wait, why is it 3 and not the not mu?
Oh
which
yeah,
is-
thank you, yes, thank you. The mean is 6. 6, 6, 6. So 4 plus 1 plus 9. Result 14 over 3. Is 14 over 3 the same as 4.7? Exactly the same. 14 over 3 or 42 over 9. 4.7. All right, so this is an example about or proving that the mean or the average of all the sample variances is the mean of all the sample variances is equal to the population variance. So, to conclude this section, we're gonna now say at the end that we have unbiased estimators. Unbiased estimators. Unbiased estimators are estimators that target the population parameter. So earlier we said that the sample means will lead you to the population mean. They target the population mean. We said that earlier that the mean of the sample means is equal to the population mean. So X bar, because it's clustered or concentrated about the population mean, it is considered statistically an unbiased estimator. It can be used to determine or to estimate the population mean, which is a good result that we're going to use later on in estimating population mean. Remember, the goal of statistics is to find more information about the population. Also, the same thing for the sample variances. Sample variance is a statistic that targets the population variance. So we have a statistics that will lead us to a population parameter. Again, we showed that the mean of the variances is the population variance. Also, we can show, number 3, that the for some degrees, of certain degrees, and with some restrictions, the sample standard deviation targets the population standard deviation. But here there is some debate or there is some concern about this thing, because this is not always true. In large samples it is true, but not with small samples. But I can still say that in general that the sample standard deviation will enable us, will lead us to estimate, it can be used to estimate the population standard deviation. And there is another one, guys, number 4, which is p hat. I haven't talked about p hat yet. This is called the sample proportion. We will discuss this in the next chapter. And it is also an unbiased estimator. And the sample proportion will always lead us to the population proportion. Population proportion. We're going to again discuss this statistic or this parameter in detail in the next chapter. These are the 4 sample statistics that can be used to estimate population parameters, right? They can be used to give us a good value a very close value to the real value, to the actual value of the population parameter. Estimation, guys, will be discussed in detail in the following chapter. Okay, any questions? All right. No questions, guys, on this topic? All right, the last section. 6.4. The central limit theorem. Very important theorem that is the foundation for a lot of statistical methods. Here's the statement of the theorem. It talks about the sampling distribution of sample means, the sampling distribution of X bar. The theorem says that for all samples of the same size with n greater than 30, if the sample size is greater than 30, then this theorem says that the distribution of X bar, the sampling distribution of X bar, can be approximated by a normal distribution. Very important result, the distribution of the sample mean, with a mean that is equal to the population mean and standard deviation that is equal to the population standard deviation divided by the square root of n. Okay, so let me explain a little bit more. If n, if the sample size n is greater than 30, right, then the distribution of the sample means of X bar can be represented by a normal distribution, bulk shape, the distribution of the sample means with the center of the distribution is or the mean of the sample means, or the center of the distribution is the population mean. Not only that, and the spread of the sample means, or the standard deviation of the sample means, is the population standard deviation divided by the square root of n. Okay, so as long as the sample size is greater than 30, we can say that the sampling distribution of sample mean is a normal distribution with a mean that is equal to mu, the population mean, and the standard deviation of this sampling distribution is the population standard deviation divided by the square root. Okay. Any questions, guys, on this? Let me add one more thing to our notes here. If all possible samples, all possible simple random samples of size n are selected from the population with a mean mu and standard deviation sigma, then the mean of all sample means and the standard deviation of all sample means is equal. The mean of the sample means is the population mean, and the standard deviation of the sample means is the population standard deviation divided by the square root. That's the theorem, guys, and let me show you how we're going to apply it. Okay, examples. Given test scores have a normal distribution with mean that is equal to 70, let's say 70, and standard deviation that is equal to 4. Right? We would say we give a population of students standard test. We found that the average or the mean value is 70, standard deviation is 4. Okay, first part of the example. See here, only one test score is selected at random. Find the probability that this test score, this single score, one test score, is greater than 74. Right? Just one single value. We did that in the previous section, right? We talked about the distribution of test scores or distribution of data values. Our test scores have normal distribution. This is the distribution of X. The center is 74. This is the population mean. I'm sorry, 70. And the standard deviation is 4. That's the distribution of X, the test scores. Now, what about the probability? What is the proportion of test scores that are greater than 74? Meaning this area, right? This area, all this area here, representing all the test scores that are greater than 74. With me? Let me put the 74 right here. So what is the probability that if we randomly select one test score, its value is 70 high, more than 74? We use what? Normal CDF, right? And we go from 74 to infinity. Or we just say instead of infinity, we say what? 9,999. And the standard deviation, I'm sorry, the mean is 70 and standard deviation is 4. Right? If we select one test score, what is the probability that this test score is greater than 74? The answer is normal CDF. I'm using my calculator. Guys, remember what we did yesterday? Normal CDF. And then 74, infinity, 9999. Center is 70. Standard deviation is 4. Enter, enter. 0.1587, approximately in percent form, 15.9%. All right. Now look at the second part. A sample of 9 students or 9 test scores is selected at random. Nine test scores selected at random. Find the probability that the average average of these 9 test scores, or the mean of the 9 test scores, X bar, not X, X bar is greater than 72. Right? So the mean, the average of these 9 test scores, what is the probability that the mean of the sample is greater than 72? In this case, we're going to apply the central limit theorem. We're going to use the sampling distribution of the sample mean of X bar. Again, the distribution of the sample mean is a normal distribution with a center that is equal to the population mean, which is in this case 70. The center is 70, and the standard deviation of the sample means is the population standard deviation divided by the square root of n. The population standard deviation is 4 divided by the square root of 9, because I'm talking about here we have a sample of 9 test scores. So 4 over 3. That's the standard deviation of the sampling distribution of X bar. So now, what is the probability that X bar is greater than 72? Again, I'm going to say normal CDF. What? 72, infinity, with a center exactly 70, and standard deviation of 4 over 3. Not 4, but 4 over 3. We're using the sampling distribution of sample mean. So I put these numbers in my calculator. Normal CDF. 72 is the lower limit. Upper limit is 999. The mean is 70, but the standard deviation is 4 over 3. I change the value of sigma, and then I enter, and I get 0.0668, and that becomes 6.7%. Completely
Professor?
different percent. Yes.
When you were finding the mean of the variances, I believe, sigma x bar, when with sigma being equal to 4, where did that 4 come from?
Yes, it's right here in the problem.
Okay, got it. I didn't see that. My apologies.
Yeah, no problem. This is given. I give you the population mean, and I give you these population standard deviation. And then I took the population standard deviation divided by the square root of n to get the standard deviation of the sample mean. So guys, notice here, when we talk about a sample mean, what is the chance that the sample or the sample mean or the average of these 9 test scores is greater than 72? It is 6.7%. In the first part, we're talking about a single test score, just one X value. What is the probability that that test score is greater than 74? That's the answer. So when we talk about single values, we use the distribution of X. And when we talk about samples, probability of samples, then we use the sampling distribution of sample mean. Okay. One more example on this. A sample of 16 test scores is selected at random. find the probability that the sample mean, the average of these 16 test scores is greater than 72. Again, I'm interested in finding the chance, the probability that the average of these tests, of these 16 test scores is greater than 72. In this case, again, I'm going to use normal CDF, again from 72 to infinity, and then the center is 70. But what now? What about the standard deviation of the sample mean? In this case, it is the population standard deviation divided by the square root of n, 4 over the square root of 16, 4 over 4, which is 1. So here I'm going to put 1 for the standard deviation. Standard deviation for these samples. And the result is, I'm sure it's going to be much lower percentage. Normal CDF 72, 999, 70, and then this is 1. Enter. Get 0.0227, or actually 8, and that means 2.3%. So again, guys, notice every time the sample size changes, the standard deviation of the sample mean changes. It's dependent on the sample size. The center still the same as the population, doesn't change in all of them. But here, this is the standard deviation of test scores for single test scores, the distribution of X. This is the standard deviation for samples of 9 test scores, and this is the standard deviation for samples of 16 test scores. Any questions, guys, on the concept of the central limit theorem? All right, good. So let me see. Final example, guys, so we can conclude this session. Assume that female or females have pulse rates that are normally distributed with a mean of 74 beats per minute and standard deviation of 12.5 beats per minute. Okay. If one adult female is randomly selected find the probability that her pulse rate X is between 78 beats per minute and 90. For one female adult, what is the probability that her pulse rate is between 78 and 90? Answer: normal CDF, right? Because the distribution of pulse rates is normal. Lower limit is what? 78. Upper limit is 90. We're going from 78 to 90. What is the center of the distribution? What is the mean? 74. And the standard deviation is 12.5. 12.5. Right? We're talking about one adult female. Let's find out what the probability is. $78, upper limit 90, 74, and 12.5. 0.2742, 27.4%. Okay, now, if 16 female adult females are randomly selected find the probability that they all of these 16 have a pulse rate with a mean X bar greater than 78 and less than 90. Right? find the probability that they have pulse rates with the mean, the X bar, between 78 and 90. Calculations, normal, CDF, 78, 90. The center is still 74, but the standard deviation of the sample mean in this case is what? 12.5 over the square root of 16. Let's figure out what this value is. 12.5 over 4 square root of 16, 3.125. And then I put this in the calculator. $78, $90, $74, 3.125. Enter. 0.1003, 10.0%. All right, guys, please make sure you complete the homework assignments. Make sure you look at these problems, study those problems, understand the solutions, review them if you have solved them, review the notes. And tomorrow we're gonna do chapter 5 and 6 test. Chapter 5 and 6 at 3 p.m. So let's meet 5 minutes, few minutes before, so we can start exactly at 3. Any questions?
Yes, Professor, just the question I asked earlier for section 5.1, number 19.
Oh, yes, thank you. Yeah, section 5.1, which problem?
19.
19, okay. All right, no problem. Let's go over it. So number 19, we're going to be referring to this table. This table describes results from groups of 8 births from 8 different sets of parents. X is the number of girls among 8 children. Okay, and X is the number of girls, so the minimum value for X is 0, 0 girls, and all the way to 8. 8 children, 8 girls, and 8 children. And these are the probability values of these number of girls. So, number 19, part A. Find the probability of exactly 6 girls and 8 boys. You're going to go to this value, 6 girls. What is the probability of that value? It is in the table, 0.109. And we're done.
Okay.
Second part, what is the probability of 6 or more girls, meaning 6 or 7 or 8? So in this case, you're going to add these 3 values, the 6 girls, 7 girls, and 8 girls. You're going to add these. So 0.109 plus 0.031 plus 0.004. Plus 0.031, 04, 0.144. And the last part, which probability is relevant for determining whether 6 is significantly high number of girls and 8 births? Is it A or B?
Is that the one where we do what's the standard deviation minus 2 times the mean or something like
Yeah,
that?
so what are you gonna do? You're gonna find the range of 2 standard deviations, right? So you're gonna find the mean minus 2 standard deviation and the mean plus 2 standard deviations. And when you find the mean, remember the mean, you have the formulas I gave you, right?
Mm-hmm.
The mean is the sum of each x value times p of x, and the standard deviation is the sum or the square root of the sum of x minus the mean squared times p of x. Once you get the mean and standard deviation, you find the mean minus 2, standard deviation, mean plus 2. And if the 6, what is it? If x is 6 falls in this range, then it is not significant. If it is, if it's outside the range, then it is considered significant.
Real quick, Professor, on the standard deviation formula that you put here, do we also minus mean square, or is this the formula?
No, just you mean this part here?
Well, everything that you have there,
Yeah.
would also minus mean square. Because what I got in my notes, unless I copy it wrong, is the standard deviation is equal to square root of the sum.
Oh, I see. No, actually, there are two formulas in the book. I'm using one of them. This is one of them here.
Okay.
Let me show you here. Hold on. Oops. So here, all right, see the variance?
Mhm.
This one here. That's the variance.
Okay.
If you take the variance, you want to find the standard deviation, you just take the square root of the variance. And that's my formula that I have here. I usually use this one.
Okay.
Now, your formula that you have is also correct, but you are using this one here.
Right. Yeah, that's the one I was looking at.
Yeah. So it's either one. You can use either one, and you will get the same standard deviation.
Okay.
Yeah. So this one here, you take the x squared. You have to square each value, multiply by the probability, find the sum, and then subtract the mean squared. I usually don't use. I use this one here, the first one.
Okay.
Yeah. Now the book also. Let me show you one more thing, Brandon. You see the. It's talking about whether 6 is significant or not. If you take those probability values, oops, if you take those 3 again and add them, if the sum of these values is less than 5%, then the 6 is not significant.
Mm-hmm.
But if it is, I'm sorry, the 6 is significant. But if it is more than 5%, then the 6 is not significant. So let's add them. Well, I think we added them earlier, which is we got what, 14.144, which is 14.4%, right? Which is more than 5%.
Mm-hmm.
So I can conclude right away that this value 6 is not significant because it has a high probability.
Okay.
Yeah. But on the test tomorrow, you're gonna use the this here, the mean minus 2 standard deviation and the mean plus 2 standard deviation.
Okay.
Okay.
And when we look at it that way, we just look at where once we get those two, we just look at where the values fall, and depending on that,
Exactly. Yes.
we determine. Okay.
That will determine that.
Okay, then. I think
right.
I might have a handle on it now.
Okay, good.